All right, everyone, get ready for today's deep dives. We're
Yeah,
taking a trip into the world of logarithms.
sounds a bit daunting.
Yeah, I know the word itself might make you want to grab a calculator,
Mm.
but trust me, stick with us. It's going to be fascinating, I promise.
Definitely fascinating.
So, you sent over some material on logarithms,
Mm-hmm.
and wow, it's dense stuff.
It can be, yeah.
It's packed with really intriguing concepts, though.
Yeah.
'Cause what we're going to try to do is break it down, pull out the most interesting bits.
Absolutely, yeah.
And by the end, hopefully you'll feel like you actually get logarithms.
Yeah.
So you ready to dive in?
I am, definitely. Let's do it.
Okay, great. Let's start with the basics. What is a logarithm? I mean, like the material defines it as the exponent a base must be raised to in order to get a given number.
Right.
That's a bit of a mouthful, isn't it?
It is, it is. It's a lot of words to sort of unpack. Maybe think of it like this. Instead of asking, what's 2 multiplied by itself 4 times, which is 2 to the power of 4 equals 16. A logarithm kind of asks, like, 2 raised to what power equals 16, and that what power is the logarithm. So in this case, log base 2 of 16 equals 4.
Okay. I
That's
like that. It's like we're solving a puzzle. You're trying to figure out that missing piece, the exponent.
Exactly. It's like that missing piece.
Yeah, I see. The material also gives some other examples, like 3 to the power of 5 is 243, so log base 3 of 243 equals 5.
Right? Yeah.
It's certain to, click for me.
It is. It is. And those examples also show you the key players involved, right? The base and the argument.
Okay, yeah.
So the base, the number being raised to a power, and the argument is the result you're trying to get.
Right, okay.
And the material does emphasize some important restrictions on these guys. Like the base has to be positive, but not equal to 1.
Right.
And the argument also has to be positive.
Okay, I see. So those restrictions make sense. Like, for example, you can't raise a negative number to a power and get a positive result.
Right. Yeah, exactly.
So we've got the basic idea kind of down, but then the material jumps into this thing called the fundamental logarithmic identity,
Yeah.
which sounds pretty grand.
Yeah, it does, doesn't it?
Yeah.
It sounds very important. And in a way it is, think of it like a superpower equation, right?
Okay.
So a raised to the power of log base a of n equals n.
Okay.
Basically, the logarithm and the exponentiation sort of, they cancel each other out. You're left with the original number.
Okay.
It's like they're like opposites. They undo each other.
So it was like a math magic trick.
In a way, yeah, I like that. A math magic trick.
The material also lists these like deductions from this identity.
Yeah.
Like log base a of 1 always equals 0. Log base n of n always equals 1, and log base 1 n of n always equals medic 1. They seem surprisingly neat and tidy.
They are. Well, let's break it down a little. Take the first one. Log base a of 1 equals 0. Remember we said a logarithm is basically asking what power do we raise the base to get the argument? Well, any number raised to the power of 0 equals 1.
Right.
So no matter what the base is, log base a of 1 will always be 0.
That makes sense.
Yeah.
Any number to the power of 0 is always 1.
Yeah.
So yeah, the logarithm has to be 0 to make that work.
Exactly.
What about the second one? Log base n of n equals 1.
Yeah, this one's pretty straightforward too. Any number raised to the power of 1 is just itself.
Right.
Right. So if the base and the argument are the same,
Yeah.
the logarithm is simply asking what power do we raise n to get n, and the answer is 1.
Right.
Oh.
Yeah. Okay, I'm with you. Okay, so what about the third one? Log base 1 over n of n equals negative 1. That one seems a bit more complex to me.
It does, but it really highlights the concept of reciprocals. So the reciprocal of a number is 1 divided by that number. So the reciprocal of n is 1 over n. And a number raised to a negative exponent is the same as its reciprocal raised to the positive version of that exponent. So for example, 2 to the power of negative 3 is the same as 12 to the power of 3. So for log base 1 over n of n, we're asking what power do we raise 1 over n to get n? And the answer is maga 1, because 1 over n raised to the power of magus 1 equals n.
Okay. That one took a moment to sink in. But I see how it works. It's amazing how these seemingly complex ideas actually have a pretty clear logic behind them. So far, so good. What's next in our logarithm adventure?
Well, now that we've sort of got the basic definition and that fundamental identity down,
Yeah.
let's look at how logarithms kind of interact with each other. The material calls these the principal properties of
Ooh,
logarithms.
principal properties. That sounds important.
It does sound important.
Yeah.
And it is. These properties, they show us how to manipulate logarithms of products, quotients, and powers. They're like special rules that make working with logarithms a lot easier.
Okay. I'm intrigued. Let's unpack these rules one by one.
Sure.
What about the logarithm of a product?
Okay, yeah. The logarithm of a product, this basically tells us that log base a of m times n
Yeah.
is equal to log base of m plus log base a of n. In other words, the logarithm of a product is the sum of the logarithms of its factors.
So if we know the logarithm of two separate numbers, we can just add them together to find the logarithm of their product.
Right, exactly.
That's handy.
Yeah, it is. It's pretty neat.
Yeah.
And then we have the logarithm of a quotient. So this states that log base a of m divided by n equals log base a of m minus log base a of n. So the logarithm of a quotient is the difference of the logarithms.
Got it. So to find the logarithm of a fraction, we subtract the logarithm of the denominator from the logarithm of the numerator. Like, these properties are giving us shortcuts.
They are. They're definitely shortcuts. They're meant to simplify things.
Yeah.
And finally, we have the logarithm of a power. So this one says that log base a of m raised to the power of x equals x times log base a of m. So the logarithm of a power is the exponent times the logarithm of the base.
So if you have an exponent inside a logarithm, you can just bring it down and multiply it in front.
Yeah.
That's interesting. It's like we're rearranging the pieces of the puzzle.
Exactly. You're rearranging things to make them simpler, to make them easier to work with. And all these properties, they really do make complex calculations a lot simpler. Like, for instance, let's say you needed to calculate the logarithm of a massive number, and this number is a product of several smaller numbers.
Yeah.
You could use the property to just break it down into smaller, more manageable logarithms.
So instead of one, like, giant calculation, we could just do a few smaller ones and then combine the results.
Yeah, exactly.
That's smart. The material mentions these properties being used in fields like finance and physics. What kind of real-world problems do they help solve?
Well, in finance, for example, logarithms are used to calculate compound interest.
Oh, okay.
Right.
Yeah.
So they help us understand how investments grow over time. And in physics, they're used to model radioactive decay.
Right.
So they help us determine, like, the age of ancient artifacts or to predict the half-life of radioactive materials.
Wow. So logarithms are more than just, like, theoretical concepts. They're actually used to solve practical problems in all sorts of fields.
Absolutely. They underpin a lot of stuff that's happening in the world.
This is already shaping up to be much more interesting than I remember from my school days, that's for sure.
Yeah.
What else does the material have in store for us?
Well, there's this really useful concept called the base-changing theorem.
Uh-huh.
It might sound kind of technical,
Okay.
but it's really a neat trick for working with logarithms.
Okay, I'm all ears. What's this base-changing theorem all about?
Imagine you have, like, a universal translator for logarithms. That's essentially what the base-changing theorem is.
Okay.
It states that log base a of m divided by log base a of b equals log base d of m.
Wait, so we can actually change the base of a logarithm?
You can.
Like, what would be the point of doing that?
Well, sometimes you need to work with logarithms in a specific base.
Okay.
For example, most calculators, they only have buttons for common logarithms, which use base 10, and natural logarithms, which use base e.
Right. The material mentioned those. So it makes sense that we might need to, like, switch between bases depending on the situation.
Yeah, exactly.
Yeah.
And the base-changing theorem gives us the power to do just that. It's like having a secret weapon in your logarithm toolkit.
I'm definitely starting to see how these pieces fit together.
Yeah.
We've got the basic definition,
Uh-huh.
that powerful identity, the properties for manipulating logarithms.
Right.
And now this base-changing theorem to, like, switch between bases.
Right.
So what's next? Do we actually get to use all this knowledge to solve some problems?
We do. The material is full of examples of logarithmic equations and inequalities.
Okay.
And these can seem tricky at first.
All right. I'm feeling brave.
Right.
Bring on the equation.
Okay, all right. But once you understand the properties and you can apply them strategically,
Yeah.
they become much more manageable. Let's start with this equation.
Okay.
Log base 2 of x squared minus log base 2 of 2x equals 3 times log base 3 of 3 minus log base 3 of 6.
Okay, that looks a bit intimidating at first glance, I'm not going to lie. What's a first step?
First, we need to make sure that any solution we find doesn't violate those domain restrictions we talked about earlier.
Okay.
In this case, x has to be greater than 0 for the logarithms to be valid.
Right, right. We can't have any negative arguments.
Exactly.
Yeah. So how do we start simplifying this equation?
Well, on the left side, we can use the quotient property to combine those two logarithms.
Right.
Remember, we said log base a of m divided by n equals log base a of m minus log base a of n.
Okay, so log base 2 of x squared minus log base 2 of 2x becomes log base 2 of x squared divided by 2x,
Right.
which simplifies to log base 2 of x over 2.
Excellent, excellent. And on the right side, we can use the power property.
Okay.
Remember, log base a of m raised to the power of x equals x times log base a of m.
Right.
So 3 times log base 3 of 3, that can be rewritten as log base 3 of 3 cubed.
Right.
Which is just log base 3 of 27.
Okay, so now our equation's a bit tidier. Log base 2 of x over 2 equals log base 3 of 27 minus log base 3 of 6. Now what?
Well, now we can use that quotient property again on the right side to combine those two logarithms.
Right.
So log base 3 of 27 minus log base 3 of 6 becomes log base 3 of 27 over 6, which we can simplify to log base 3 of 9 over 2.
Okay, so we've got log base 2 of x over 2 equals log base 3 of 9 over 2. But now we have, like, different bases on each side. Yeah. How do we deal with that?
That's where our trusty base changing theorem comes in.
Right.
It lets us change the base of either logarithm to match the other.
Okay.
Let's change the base of the right side to 2.
Okay.
So using the base changing theorem, log base 3 of 9 over 2, that becomes log base 2 of 9 over 2 divided by log base 2 of 3. Now, both sides of the equation have the same base.
Right, okay. And since the bases are the same, we can just equate the arguments.
Yeah.
So that gives us x over 2 equals 9 over 2 divided by log base 2 of 3.
Exactly. So by changing the base, we were able to kind of simplify the equation, isolate x. And from here, it's just, basic algebra to solve for x.
Okay.
Right. Multiply both sides by 2. And we get x equals 9 divided by log base 2 of 3. And since x is positive, this solution fits our domain restriction.
Wow, we solved it. It's pretty amazing how these properties and theorems work together like puzzle pieces, to help us solve these equations. I'm starting to feel a lot more comfortable with logarithms now.
I'm glad to hear that.
But what about inequalities? Are they similar?
Yeah. The approach is similar, but we need to be extra careful with the direction of the inequality.
Right.
Do you remember how we talked about the relationship between the base and the argument?
Yeah.
And how that affects whether the logarithm is positive or negative?
Right. If the base and the argument are both greater than 1, or both between 0 and 1,
yeah,
then the logarithm is positive.
Uh-huh.
But if 1 is greater than 1 and the other is between 0 and 1, the logarithm is negative.
Exactly. So when we're solving inequalities, we need to consider different cases.
Right. Depending
on whether the base is greater than 1 or between 0 and 1. And we might need to flip the direction of the inequality depending on the situation.
Got it.
Let's look at an example to kind of make this a bit clearer.
Bring on the inequality.
Okay. So consider this one from the material. Log base 1 over 3 of x squared minus 6x plus 18 minus 2 times log base 1 over 3 of x minus 4 is less than 0.
Okay, so this one involves subtraction, and it even has a coefficient in front of one of the logarithms.
Yeah.
Where do we even begin with this?
Well, as always, let's start with our domain restrictions.
Okay.
The arguments of both logarithms must be positive. So x squared minus 6x plus 18 must be greater than 0, and x minus 4 must be greater than 0.
Right. No negative arguments. So we need to solve those inequalities first to figure out, like, what values of x are even allowed.
Exactly.
Yeah. Okay, so if we solve those inequalities, we find that x has to be greater than 4.
Right.
So that's our valid domain for this problem.
Exactly, yeah.
Okay, so x greater than 4. Got it.
Yeah.
Now, how do we tackle the actual logarithmic inequality?
Okay, well, we'll notice that the base of both logarithms is 1 over 3, which is less than 1.
Right.
Right. This means we need to be very careful with the direction of the inequality.
Okay, so how does having a base less than 1 change things?
Well, when we apply the properties of logarithms and the base is less than 1,
Yeah.
we need to flip the inequality sign.
Okay.
Right. Think of it this way. With a base less than 1, a bigger argument actually leads to a smaller logarithm.
Fantastic.
It's like a mirror image of what we're used to.
Okay, so we need to keep that flipping rule in mind as we simplify the expression. So what's our next step?
Well, on the left side, we can use that power property to rewrite 2 times log base 1 over 3 of x minus 4 as log base 1 over 3 of x minus 4 squared.
Right, we can bring that exponent of 2 down in front
Yeah.
and multiply it. So now our inequality looks like this. Log base 1 over 3 of x squared minus 6x plus 18 minus log base 1 over 3 of x minus 4 squared is less than 0. Now what?
Now we can use the quotient property to combine those two logarithms.
Okay.
But remember, since the base is less than 1, we have to flip that inequality sign.
Right.
Right. So our inequality becomes log base 1 over 3 of x squared minus 6x plus 18 divided by x minus 4 squared is greater than 0.
Okay, I see how we flip the sign there. Because of that base being less than 1, so how do we figure out when this logarithm is greater than 0?
Well, remember that log base anything of 1 equals 0.
Right.
And since our base is less than 1, the logarithm will only be greater than 0 when the argument is less than 1.
That makes sense. So we need to solve the inequality x squared minus 6x plus 18 divided by x minus 4 squared is less than 1.
Exactly.
Okay.
And we can simplify this even further by multiplying both sides by x minus 4 squared. Right. We know this quantity is always positive since x is greater than 4.
Right.
So we don't need to flip the inequality sign.
Okay.
This gives us x squared minus 6x plus 18 is less than x squared minus 8x plus 16.
Okay. Now it's just a matter of like combining like terms and solving for x. Let's say we get 2x is less than -2, which means x is less than -1.
But hold on. We have to remember our domain restriction,
Oh,
right? X must be greater than 4.
Oh, right. So this solution doesn't actually work because it falls outside our allowed values for x.
Exactly. That means there are no solutions within our valid domain. The inequality log base 1 over 3 of x squared minus 6x plus 18 minus 2 times log base 1 over 3 of x minus 4 is less than 0, has no solutions for x greater than 4.
Wow. That was a tricky one. I can see how easy it would be to like forget about the domain restriction or that flipping rule for bases less than 1.
Yeah.
It really emphasizes how we need to pay attention to all the details when we're working with logarithmic inequalities.
Absolutely. You got to keep track of everything. It's all about understanding the properties and applying them, carefully.
So we've covered equations and inequalities.
Yeah.
What's left to explore in the world of logarithms?
Well, the material also mentions graphs of logarithmic functions.
Okay.
Visualizing logarithms can really help to solidify our understanding.
Graphs. Now those I remember, especially their unique shapes. The material says that the shape depends on whether the base is greater than 1 or between 0 and 1.
Right.
Yeah.
When the base is greater than 1,
Yeah.
the graph starts low on the left,
Okay.
crosses the x-axis at 1, 0, and then it gradually increases as x gets larger.
It's like a ramp gently sloping upward.
Exactly.
Right.
Exactly. But when the base is between 0 and 1,
Yeah.
the graph kind of starts high on the left, crosses the x-axis at 1, 0, and then gradually decreases as x increases.
So it's like a slide sloping downwards.
Precisely. And no matter what the base is, all logarithmic graphs have a vertical asymptote at x equals 0.
Meaning the graph gets closer and closer to the axis, but never actually touches it.
Exactly.
Yeah.
And these graphs can be really helpful for understanding the relationship between input and output values for logarithmic functions.
Yeah, I can definitely see how visualizing these graphs could make the concepts more intuitive. It's like seeing the logarithm come to life,
It is. It's a way to move beyond the numbers and the equations.
Yeah.
And to kind of see that bigger picture of how logarithms behave.
This has been such a fascinating deep dive into the world of logarithms.
Yeah.
It's incredible how much depth there is to this topic that I totally missed back in school. I'm feeling a lot more confident, even like excited about logarithms now.
That's great. That's really what it's all about, right? And always rewarding to see someone discover the beauty and power of mathematics.
Okay, so we've covered a lot of ground. The basic definition of a logarithm, that fundamental identity,
Mm-hmm.
the properties for manipulating them, the base changing theorem, and even how to solve equations and inequalities.
Hmm.
And we even touch on how visualizing the graphs can deepen our understanding. Before we wrap up, what are some key takeaways you'd like listeners to remember from this deep dive?
Well, first and foremost, I'd say remember that logarithms are exponents in disguise.
Okay.
They provide a different way of looking at the relationship between numbers and their powers. And don't be intimidated by the notation or the rules. Once you understand the underlying logic, it all starts to kind of click into place.
Right.
Yeah.
Right. It's all about those relationships between exponents and bases and arguments and the properties we talked about. Those are like our secret weapons for simplifying calculations and solving problems.
Exactly. Yeah. And don't forget about that base changing theorem, right? It gives us the flexibility to work with logarithms in any base that we need.
It's amazing how all these concepts connect to form a coherent framework for understanding logarithms.
Yeah.
You know, they're not just like abstract mathematical ideas. They're actually like powerful tools for solving real world problems.
Yeah.
I'm already starting to see logarithms in a new light.
That's fantastic. That's fantastic. And that's what makes exploring mathematics so rewarding, right? It's about uncovering the patterns and the connections that underlie the world around us.
Well, this has been an incredible journey. Before we say goodbye, I want to leave our listeners with a final thought. Now that you have a foundational understanding of logarithms, think about how they show up in everyday life.
That's a great point. Yeah. Logarithms are everywhere. From the Richter scale for earthquakes
Yeah.
to the pH scale for acidity,
Right.
from measuring sound intensity
Yeah.
to calculating compound interest. They're silently working behind the scenes, helping us to understand and quantify the world we live in.
Exactly. Yeah. Keep your eyes open, and you'll be surprised how often logarithms pop up. You might even start to see them as more than just mathematical symbols,
Yeah.
but as a language for understanding patterns and relationships in the world.
I love that. It's like learning to decode a secret language that unlocks a deeper understanding of the universe.
Yeah. This deep dive has completely changed my perspective on logarithms. A huge thank you to you for guiding us through this fascinating world.
It's been a pleasure. It's been a pleasure.
And to our listeners, we hope this episode has sparked your curiosity and give you a newfound appreciation for these powerful mathematical tools. Until next time, keep exploring, keep learning, and keep diving deep.
So let's look at one more inequality to really solidify those ideas about bases and arguments.
Okay, yeah, I'm ready for a final challenge.
All right, let's try this one. Log base 0.5 of x squared minus 5x plus 6 is greater than -1.
Okay, so we have a base of 0.5, which is less than 1. And I know we need to be like extra careful with the direction of the inequality in these cases.
Exactly. But as always, we start with our domain restrictions.
Right.
The argument of the logarithm x squared minus 5x plus 6 has to be strictly greater than 0.
Right. No negative arguments or zeros. So we need to solve that inequality first to see what values of x are even allowed.
Right. And we can factor that quadratic expression to get x minus 2 times x minus 3 is greater than 0.
Oh, right.
This tells us that the expression is positive when x is less than 2 or if x is greater than 3.
So those are the values of x that satisfy our domain restriction.
Exactly, yeah.
Now, how do we tackle the actual logarithmic inequality?
Okay, well, we'll remember that with a base less than 1,
Yeah.
as the argument of the logarithm gets bigger, the value of the logarithm actually gets smaller.
Right.
It's like they're moving in opposite directions.
Right. So a larger argument leads to a smaller logarithm when the base is less than 1.
Okay.
Yeah.
I'm starting to see the pattern here.
Exactly. So if we want the logarithm to be greater than -1, we need the argument to be smaller than 0.5 raised to the power of -1,
Okay.
which is 2.
Okay, I'm following you.
Yeah.
So we need to solve the inequality x squared minus 5x plus 6 is less than 2.
Precisely.
And when we solve this quadratic inequality, we find that 1 is less than or equal to x, which is less than or equal to 4.
But we can't forget about our domain restriction.
You're absolutely right. You're absolutely right. We have to combine our domain restriction x less than 2 or x greater than 3 with the solution to the inequality. 1 is less than or equal to x, less than or equal to 4.
Right. Okay.
You're right.
So putting those together, we find that the solution has to be in the interval from 1 to 2 or in the interval from 3 to 4.
Exactly. That's the range of x values that satisfy both the inequality and the domain restriction.
Wow. That was a tricky one, but we managed to navigate through it. It really highlights how important it is to consider the base and the argument and to always be mindful of those domain restrictions.
Absolutely, absolutely. It's so easy to kind of slip up on those. But yeah, you nailed it. I feel like I've leveled up my logarithm skills today.
Yeah.
That's fantastic to hear. It's been a real pleasure diving into this topic with you. I hope our listeners have also gained a deeper understanding and appreciation for the world of logarithms.
Me
Yeah.
too. This deep dive has completely transformed my perspective on logarithms. I used to think they were just like abstract mathematical concepts,
Yeah.
but now I see them as like powerful tools for understanding the world around us. A huge thank you to you for being such a fantastic guide on this journey. And to our listeners, we hope this episode has sparked your curiosity and giving you a newfound confidence in tackling logarithms. Remember, they're not as scary as they seem.
No, they're not.
And once you unlock their secrets,
Yeah.
they can open up a whole new world of understanding. Keep exploring, keep learning, and keep diving deep.
Okay, so we tackled that last inequality. We survived.
Yeah, we did. We did. And I feel like I actually learned a lot from that.
Good. I'm glad to hear that. It's always exciting to see these concepts kind of click for people. You know, it's like we've journeyed into the heart of logarithms. We've explored their definition, those fundamental properties, the base changing theorem, how to grapple with equations and inequalities, even touched on their graphs.
Yeah.
It's been a pretty comprehensive deep dive.
It really has.
Yeah.
You know, and I think the thing that struck me the most is that logarithms aren't just some like abstract mathematical idea.
Right.
They actually have like real world applications in so many different fields. I mean, we talked about finance, physics, earthquakes, acidity. It's amazing how they kind of underpin so many aspects of the world around us.
They do. It's like a hidden language that helps us to understand and make sense of the patterns and relationships that we see in nature and in the universe.
You know, before we started this deep dive, I have to admit, I was a bit intimidated by logarithms. I had those like flashbacks to high school math class, you know.
I understand. We've all been there.
But now I actually see them in a whole new light. It's
Yeah.
it's like you said, it's like a language. And once you start to understand the grammar and the vocabulary, it opens up a whole new world of understanding.
It does. And the more you explore it, the more you'll see how these concepts connect to other areas of mathematics, to
Yeah.
science, to the world around us. So keep exploring, keep asking questions, keep diving deep into those topics that spark your curiosity. You never know what you might discover.
Well said, well said. This deep dive has been absolutely incredible. And a huge thank you to you for guiding us through this fascinating world of logarithms. And to our listeners, we hope this episode has inspired you to see math in a new way, to embrace the challenge, and most importantly, to never stop learning. Until next time, keep exploring, keep diving deep. And as always, thanks for listening.